This meeting is being recorded.
In section 10 from chapter 13, we're going to look at some of the ring opening reactions that we can use epoxides to generate. So we note here that epoxides can be useful synthetic intermediates due to their significant ring strain, right? We know that we have a three-membered ring, so we have that ring strain that can facilitate some reactions that we normally wouldn't see with both weak and strong nucleophiles. So things like Grignard reagents, hydride reagents, alcohols, or alkoxides can all react with epoxides to perform this ring opening type of process. So what we see here with a strong nucleophile, something like sodium hydroxide, in this first step, the hydroxide would function as a nucleophile. We have this nucleophilic attack. This opens the ring, and we see that hydroxide has been added to the ring, and this alkoxide ion can then be protonated using something like water here in this proton transfer step. So due to the opening of the ring being thermodynamically favored, this process would occur. We can see here that we generally do not think of alkoxides as good leaving groups, but it is thermodynamically favored due to that ring strain. So this is the graphical perspective or representation of why we can generate that alkoxide ion using a cyclic ether like our epoxide and sodium hydroxide. The energy barrier between a regular non-cyclic ether, a non-epoxide, is way too high for this to occur. And we can see that many other strong nucleophiles besides hydroxide can also be used. So we have everything here, right, from sodium cyanide, sodium thiol, Grignard reagent, the hydride reagents, all of the above here can be utilized, and we find that they would be radioselective and stereoselective in these ring opening processes. So on the next slide, we'll discuss the radioselectivity. So the epoxide ring opening is an SN2 process. We have that nucleophilic attack occur, and we'll see that the less hindered carbon is more reactive towards a strong nucleophile. So we have our two carbons here in our epoxide. The one on the right does not have substituents besides hydrogen. So that would be where the nucleophile attacks and the ring opening occurs. And this is our product that will be generated, right? So we always have the less hindered carbon being attacked by a strong nucleophile. When we talk about the stereoselectivity now, so which stereoisomer will result, since this is an SN2 process, we should see inversion of configuration. So again, we would have our less hindered spot here where the nucleophilic attack occurs. And since this oxygen was on a wedge, we see that the configuration here, now bonded to our nucleophile, would be on a dash. So we have configuration inversion. Then this would be our rule for the stereoselectivity of the ring opening of epoxides. So this is specific when we have acidic conditions used to open epoxides in addition to those strong nucleophiles. So what we here see is in this first step, we have a proton transfer. So HCl, HBr, water, or alcohol could all be used in these processes here. So first we have this proton transfer. Our epoxide is protonated in this first step, and then we see the resultant halide here, chloride or bromide, can act as a nucleophile now, and this SN2 process can occur, and the ring opening, and we have this substitution here, this nucleophilic substitution. So water or alcohol, as we mentioned, could be used as a nucleophile under these acidic conditions. So we see acid as a catalyst here in parentheses, and then we have an alcohol in this lower reaction mechanism, and then we have in the upper, we have water used. So notice the slightly different products that result as we use water. We have OH, hydroxide group, and then we have an alkoxide group added here when we use alcohol. And a common use or a common everyday product that can be made through this method of ring opening. Industrially, this compound called ethylene glycol is made using acid conditions and water. This ring opening of ethylene oxide occurs and we generate antifreeze, better known as ethylene glycol. So this is the ring opening of an epoxide under this acid catalyzed mechanism shown here. So first we have that proton transfer, we protonate our epoxide, then in an SN2 mechanism here, we see that water acts as our nucleophile, and that has performed its nucleophilic attack here. And then in this last proton transfer, we see water grabbing this proton here, and then we have created our ethylene glycol or whatever product we're trying to form through this ring opening through acid catalyzed conditions. Again, we should look at the degree of substitution. Under acidic conditions, the nucleophile will attack at the less substituted carbon. We've seen this previously. So we have a primary site here versus a secondary site here. So we see that the nucleophilic attack would occur on the less sterically hindered site. So that's where we have our nucleophile add to this epoxide after the ring opens. If we have a tertiary site, we'll see that the steric hindrance isn't our main concern, but the electronic effects now take over, and this will be explained on the next slide a little bit more. But a tertiary nucleophilic attack occurs here at this tertiary site. So why does this occur? Since the epoxide is a cation under acidic conditions, we'll see that the electronic effects overwhelm when we have a primary versus tertiary site for attack versus our dominant factor being the steric effect when we only have a primary versus secondary site on our epoxide. So note that when it's primary versus secondary, the primary site would win for a nucleophilic attack, but if it's primary versus tertiary, the nucleophilic attack would occur at the tertiary site because of that electronic effect being our dominant factor. So again, we should note that we would have an inversion of configuration because this does go through that substitution mechanism, SN2. So what we see here at our tertiary site, if it happens at a chirality center, we have this methyl group that was on a dash. Notice that the methyl group is now on a wedge, and our nucleophilic attack has been added now. Our alkoxide, rather, has been added on a dash. So whenever we have a chiral center, we should note inversion of that configuration. So we'll continue with the next section in our next video.